So you'll have access to the slides and stuff. And I need.
And this funky recording, hopefully, I have no idea if it's working or not.
So I'm gonna go first.
Hopefully, this is my first time trying to record a lecture here, so, yes, if it works, yes, if it doesn't, no.
What is a camera?
Well, it's supposed to be that easy, it's supposed to be, you hit the big button that says start recording,
Is
this
it
is
just a
faculty.
screen capture?
Yeah, the whole room, if you saw the screen, it shows the room, this is the camera right here.
Oh.
So it's got one of those fisheye
okay.
ones, so it's supposedly doing everything.
So it's like recording me right now.
And it's recording the screen, like the slides and everything, so. If it works, it's gonna be amazing. So yes. But we will definitely do the slides, if nothing else.
Why can't I find the file explorer? Okay. I haven't given a talk in person in so long. Oh my god.
I'm very rusty.
Yeah, so I just have to say, like, if I'm rusty or a little weird, this is actually meeting with you all is the first time I've met with people since last February, probably.
Yep.
At my university, we're still all remote, so just bear with me.
Did you hear that U of I is requiring vaccinations
did.
of all their students this morning? He announced that.
Maybe that's
Yeah, I know, because we had asked about that earlier and they said, oh, no, we can't, it's only the private schools, and now it's.
That's not true. I stayed in UC system.
I know, so SUNY too. Mm-hmm.
I brought that up and I'm like, so maybe. Okay, sorry.
It's okay. All right, so this is what it's like to talk in front of people again. So I'm going to talk a little bit about the groundwater chemistry and nutrients project. And working on it with me is Diani and also Vanessa Vasquez, who will be joining us in Mexico, who was part of the group last year. So some of the questions that we look to answer here are, we're really interested in two elements, nitrogen and phosphorus. Okay, and we want to not just know how much nitrogen and phosphorus there are in the area, and I'll talk about why that's important, but we want to know what kinds of nitrogen and phosphorus, because it's not like there's just like elemental nitrogen and elemental phosphorus. It exists in different forms, and those different forms are going to tell us quite a bit about the groundwater quality and what's going on in the cenotes. So when nitrogen and phosphorus are nutrients, right? They feed plants, right? They're important for animals. So I'll be referring to them as this group of nutrients. And we also, we want to know what the major forms are. But when we get down to a little more detail, we want to know how do those different nutrients vary with depth within the cenote, right? Because the conditions change, as I'll talk about, from the surface as we go down in depth in water, we would expect these forms to change as well. We might have, one type of nutrient that contains nitrogen is nitrate. We might have nitrate near the surface, but as we go deeper and as conditions change, we might see another form called ammonia. So we want to be able to look at that. And what are the main geochemical controls on the different forms of nitrogen and phosphorus? So there's different types of things that we can measure or infer, like pH and redox state, that are going to control what kinds of nitrogen and phosphorus we see. And then once we have that data, right, then we can start to think about, well, where is this nitrogen and phosphorus coming from? Now, I use the word nutrient pollution here because that's a real thing. That can happen. We'll talk about some sources of that. But it's also important to remember that nitrogen and phosphorus can have non-anthropogenic input, right? That they can come from natural sources. So that's where we start to look into our data and we start to really kind of analyze it. And then relate the biogeochemistry of the nitrogen and phosphorus to the other projects, right? So if somebody's doing microbiology, human activities, those sorts of things, and then overall to the composition of the aquifer, right? Do you all know what an aquifer is? Okay, so an aquifer is just the place below ground where water is stored. It's stored in rocks, usually. And just as a little bit of, before I get into it, right? The cenotes that we see that are open to the sky, it's actually looking down into an aquifer. You're looking at the groundwater below ground. There's groundwater below our feet right now. How deep, Mel? Do you know?
So one of the sites we have on the west end of campus, it goes about 10 feet.
Okay, so-
To get groundwater,
Okay.
the water table here.
So 10 feet, where I am in Chicago, it's actually closer to about 50 or 60 feet, right? But the cenotes in Mexico, right, you could, because like they're actually right there, right? And the way that the rock has dissolved and they're open now, that you're actually, like if you were to swim in one, you are swimming in that aquifer. So like, you know, the idea of like a well where you pull water up from, right? That water comes from an aquifer where the groundwater is stored.
So we will be visiting the groundwater and swimming in the groundwater at Rio Secreto. We'll probably do it sometime, we're leaving here on the 30th, so it'll either be the 1st or the 2nd.
I'm gonna miss it.
We'll be going and swimming in the water table.
Rio Secreto's actually really cool.
I remember, Ken, the first time we went, you were so excited to be like, I'm in the
I am always excited to go there. I'm sad I'm gonna miss it this year. So our main goals, right, are to identify what we call the major species of nitrogen and phosphorus. What are those forms, okay? We're also going to measure the major ion chemistry of the water. And when I talk about that, I mean like the main things that are dissolved in the water, things like sodium, magnesium, calcium, chloride. What are the major dissolved ions? We're also going to do some field measurements on some parameters while we're in the field, things like pH, conductivity, those sorts of things. Determine what is controlling what we call the speciation of nitrogen and phosphorus. Speciation means, okay, I know I have nitrogen and phosphorus in my water, but what types of species are present? Is there nitrate? Is there nitrite? Is there ammonia? Those sorts of things. And these parameters like temperature, pH, dissolved oxygen, those are the things that control the speciation. We're going to look for those connections between potential sources of nutrient pollution and our findings. For instance, there was one cenote that we've worked at in the past where very, very active, lots of tourists, and their bathrooms are actually up gradient from the cenote. And there's no like real sewage system or anything, so up gradient means they're uphill. So in that cenote, if things aren't working correctly, it's very possible that when the stuff, right, goes below ground or wherever it goes, then it will flow underground, but it will flow downslope and could possibly enter the cenote. So those are some of the things that we'll look at. And then we can have some fun comparing our findings with some regulatory information, right, on recreational use, but also drinking water. Because remember, this is an aquifer, this is used for drinking, but it's also used for these recreational purposes as well. So we have these two competing things, right? If we want to look at, say, what the allowable limits of nitrate are, or ammonia, or things like that. So basically, we're going to try to tell a story, right, about the chemical processes, right, that basically result in the nutrients that we find there and the types, and what that means for these aquifers, right, for this important source of not only drinking water, but recreation for our little area of the Yucatan. So the primary activities that we'll be doing, we'll be going out to the field, we'll be measuring things in the field, right, we call field measurements. We'll be sampling water for doing laboratory analyses. So we'll do some laboratory work, primarily spectrophotometry, which I'll talk a little bit about, and ion chromatography. And then we'll do data analysis, and we'll do some geochemical modeling, where we'll use thermodynamics. You all familiar with thermodynamics? Does that make anybody go, or does everybody go, yes? I love thermodynamics. I think it's just awesome. But yeah, so we're going to be using some computer programs and some simple calculations to do some geochemical modeling to try to tell that story that I talked about at the beginning. So you've probably seen this before, right? But we're going to examine an area, right, of the Yucatan Peninsula. So here is the entire peninsula here. Here's Cancun is up here. Puerto Morelos, where we're staying, is probably right around here, right? And when we zoom in on this little area, right, Cancun is here. Here's Puerto Morelos right here. We'll probably be working along this road here, okay? All of these numbers are these wells? are these cenotes?
Some of them are wells, some of them are cenotes.
Okay, so they're places where we can access the groundwater,
Yeah.
right? And this is called the Ruta de los Cenotes, so it's the road of cenotes. And so yeah, we're going to be staying right here, and that road here is primarily where we'll probably be working, right? So looking at this area in here, some of these cenotes are like, the tour buses come from Cancun, one after the other, so they're very busy. Whereas some up in here, right, as I said yesterday, are more frequented by locals, so they're not as crowded during the weekdays. On the weekends, they can become very crowded. And if we're able to, if we come out here, there's actually one that has not been open for tourism yet. So we might check that one out as well. Access is always going to be interesting. So this crazy map, right, is again the Yucatan Peninsula, and it's got all these lines and arrows and things all over it. And what these all represent, and I hope it paints the picture that it's a little confused as to what's happening there in terms of how the water moves below the ground, or how the groundwater moves. All these arrows, right, indicate different studies, okay, that have been done by different people, showing what they think is the direction of groundwater movement, okay? And if we think about it, groundwater movement is important because, let's say we zoom into an area over here, right? So here's Puerto Morelos, here's Cancun, so we're over here, right? If there's something, say here, that is, say, introducing nitrogen and phosphorus into the aquifer, we want to know which way the groundwater flows to know if areas over here or over here would be impacted by it, okay? So let's take this little example here, like this arrow goes this way, right? So if something was introduced into the aquifer here, right, they would flow in this direction towards the coast. And see these little question marks, right? That's where there's some confusion about which direction the groundwater flows. Now this is a very big scale map. We'll be focusing on a much smaller area, but I show this just to give you the idea that groundwater flow is not simple in this area, right? It doesn't just flow in one direction. This area here, right, lots of question marks, but again, our focus is going to be in here. And what's interesting, see how there's this arrow that goes up and this arrow that goes down, right? And on either side, the water goes this way or the water goes this way. That's called the groundwater divide, right? So it divides the direction of flow, right? So from here over here, the groundwater flows towards the coast, and over here it flows in the opposite direction. So we'll be using the major ion chemistry to possibly look at some more information to add to what looks like confusion on the groundwater flow. So in terms of nutrient pollution, right, one of the things that we can tell by looking at, say, nitrogen and phosphorus in our waters is that has there been an influx of organic matter, right? So that could be treated or improperly treated sewage, also these natural sources like animal waste or leaf litter. But when organic matter starts to decompose in water, it tends to release the nutrients that it has used while it was living, and that tends to be nitrogen and phosphorus are the two signs. In bodies of water that have increased nitrogen and phosphorus, you can see increased algal and plant growth. Are you all familiar with the term eutrophication? No? You cannot be, it's fine. Right? So eutrophication is the process where you have an influx of nutrients into a body of water, okay? And that causes the algae to bloom, right? They're like, cool, it's a party, all these nutrients, right? I'm gonna grow. And then the algae dies. Now when the algae dies, it becomes organic matter, which then decomposes, okay? And then one of the things that happens when you decompose organic matter is that it sucks up oxygen. That process requires oxygen. So you end up lowering the oxygen in the water. But at the same time, those algae are organic matter that are decomposing, and they release more nitrogen and phosphorus, which causes another round of growth and death, decomposition, and then another decrease in dissolved oxygen. So this process, right, can actually lower dissolved oxygen in the water. If you've heard of the dead zone in the Gulf of Mexico, right? It's this area that in the summer that basically dissolved oxygen concentrations drop to almost zero, and it causes fish kills, it kills all the animals that live there. And one of the primary sources of that is not far from here. It's that Chicago and all the cities along, say, the Mississippi River and its tributaries, well, Chicago in particular, right? We discharge our treated sewage into waters that lead into the Mississippi, and it flows all the way down to Louisiana, gets discharged into the ocean, right? That treated sewage is a big source of nitrogen and phosphorus, right? Which causes that eutrophication to occur in the Gulf of Mexico. And the same thing can occur, right, in our cenotes as well. And again, just as a reminder, just because we find nitrogen and phosphorus, it doesn't mean that it came from humans, right? As I said, decaying leaf litter, natural sources of organic matter, animal waste, those sorts of things. So those are all things that we're going to want to keep in mind as we start to do the data analysis part, is what are our sources, right? What do we think is going on there? So in terms of sampling water, right, we'll definitely sample cenotes. You can see here some students. Cenotes are nice because they tend to have these rock ledges that you can put your stuff on and work on. So just so you know, it's like a nice little natural lab. We might sample some groundwater wells in the area if we get to it. And maybe, who knows what else we might find. I always put others because it's always a surprise when you get down there, right? You know, so you make a connection with somebody and they're like, hey, I got this pond in back of my barn. Do you want to come check it out? And you're like, yeah, sure, let's go do it. So that's primarily what we'll be sampling. So how we sample is going to depend on the type of samples. If we're sampling from the surface, right, it's easy enough to have a sampling bottle, like a plastic bottle. You just bend down, scoop it up, take it, right? However, when we want to do depth-specific sampling, right, so we want to get a sample at the surface, we want to get one at 3 meters depth, 6 meters depth, 9 meters depth, we use this little doohickey called a Kemmerer sampler. And what's nice about it is that, as you can see here, right, it's got kind of a clear tube. It's got these two little plungers on the end, and it's got this contraption here. So you can lower it down into the water. You put measurements on the rope so you know how deep you've gone. And then you slide a weight down the rope. It's called a messenger. And that messenger hits this thing here, and it releases these two things. And there's a big elastic band in here, and it snaps closed, and it grabs that sample of water at depth. And then you can haul it up and do what you want with it. So this will be important when we look at what happens in the speciation of these things with depth. So just to show you how some things change with depth, okay, this is from a very deep cenote. This is not one of the ones we'll be using. But so depth is on this axis, starts at meters from 0 down to 80. And there's a couple things plotted on here. pH is the green line. Here's the scale for pH here. The blue line is electrical conductivity. Here's the scale down here. Electrical conductivity is the measure of the salinity of the water, or how much stuff is dissolved in it. And then the red line is the dissolved oxygen concentration, and it's measured in % of saturation, or how much the water can hold. And we can see how these are some of those geochemical parameters I talked about that control speciation, right? These change dramatically with depth. We see, especially if we look at conductivity, right? It's fairly low until we get down to about 50 meters, and then it just gradually increases. So that means the water gets saltier with depth, right? And I don't know if you talked about this yesterday, Mel, but the way the aquifer works, right, is that there is like a floating lens of fresh water that sits on top of salt water underneath. So in this very deep cenote, we've actually hit that saltwater interface. Other things on here that I just want to point out is dissolved oxygen, right? Dissolved oxygen near the surface, because it's exposed to the atmosphere, is quite high. But then it drops pretty dramatically, and then it does some really cool things that we hopefully will see in our measurements, right? And then stays very low. So just to give you an idea of how these things actually change with depth. I'm out of shape, I haven't done this in so long. So in terms of our field measurements, these are things we'll measure directly in the field, because if we take a sample and bring it back to the lab, they will change, right? We don't want to know what they are after we put them in a bottle and brought them back. We want to know what they are right there. So that's pH, specific conductance or conductivity, that is basically how much stuff is dissolved in the water, temperature, the dissolved oxygen content, because dissolved oxygen content, and this next one, oxidation reduction potential, these are very closely linked, and this is one of the strongest controls, especially on the types of nitrogen that we'll find in our systems, right? And it possibly might be the main control on the nitrogen speciation, maybe not the phosphorus, but definitely the nitrogen speciation, as we'll see. So we sometimes call oxidation reduction potential EH, right? You know how P is like pH, right, for acidity. E for EH is kind of the same thing, but it's for, I don't want to get into it, but it basically tells us if we're in an environment that is oxidizing or an environment that is reducing. So our field measurements, we're going to be using something called a hydrolab. It's a big, long instrument that has all the probes at the bottom, and you can lower it into the water, and it automatically records all that data as you lower it down through the water, right? So it's going to record pH, dissolved oxygen, ORP, total conductivity, and temperature.
And turbidity.
And turbidity.
I bought that one for turbidity.
Sorry.
The one I bought also has turbidity.
And what's nice is that it has a little handheld unit that all the data is automatically stored that you can then upload to a computer at the end of the day. So everything, right, that you're doing, right, is going to be stored. You don't have to worry about writing it down. Everything kind of is all in one. It will require to be calibrated every day. We're going to learn how to do that. And just regular maintenance, making sure that the electrodes are working okay and all that stuff. But again, what's nice is that you can just tie a rope to it and you can just start at the surface and very slowly lower it, and it's automatically recording those measurements to give us something that looks like this. So dissolved oxygen and the oxidation reduction potential, right? It can give us clues as to, are we close to the saltwater interface, right? Is that something that's influencing our numbers? If dissolved oxygen and oxidation reduction potential are low, are we seeing a place where the oxygen's being used up, right, to decompose organic matter, right? Again, this is that process of eutrophication, right? Organics, more breakdown, less dissolved oxygen, more reducing conditions is how it happens. And also, right, what types of nitrogen and phosphorus should be present? So, oxidation reduction potential, dissolved oxygen, and EH are all very, very closely related. You can actually, there's equations that you can connect them all, okay? So I might use those terms a little interchangeably. But in terms of EH and pH, right, those are two really big controls over what we expect to see in the water, okay? EH is a measure of the oxidation state, and it's measured in volts. pH is a measure of the acidity or alkalinity, and it's measured on the pH scale. And what we see here, right, is a very common diagram called an EH-pH diagram. We'll be working to make these using some different programs to plot our results on. And what's shown here, right, is how different types of water, right, in terms of their EH and pH, right, where they would plot on this diagram. Two important things, right, this line here, right, above this line, right, water is not stable, so we don't need to worry about that. Below this line, water is not stable. But in between these two lines, right, we see how there's this range of environments, right? So at high EHs, right, we see environments in contact with the atmosphere, exposed to oxygen. As we go down in EH, right, we're into rain, streams, oceans, and then as we get down here, these are more reducing environments, right, where we see groundwater, bog water, environments isolated from the atmosphere or waterlogged soils. Now I'm going to show you a diagram in a minute that compares this to how we expect the different forms of nitrogen that we see in our system, right? What we expect to see there. So I left this here for reference, right? So here is a diagram, an EH-pH diagram that shows the speciation of nitrogen, right? So as you can see here, there's these red lines that separate these different fields, right? Every compound in here contains nitrogen, right? But what form of nitrogen is controlled by the EH and also the pH, okay? And this is, I made this diagram using a program called Geochemistry Workbench, which we'll be using. And as you can see, first thing I want to point out, right, is down in this area, none of these compounds contain oxygen. Right? These are the reducing environments, right? We have an ammonium ion and ammonia, okay? And then another thing I'll point out, which I think makes sense, right? As I go lower in pH, are there more hydrogen ions or less hydrogen ions? Lower in pH. More, right? Acids contribute hydrogen ions to solution, right? And lower pHs are more acidic. So even just looking at these two species, right, here, right, I have 3 hydrogens in my compound. Here I have 4, right? So it kind of, I hope that helps to kind of look at these. But the important part here is that when we get up above these two, the stability fields of these two compounds, then we get into other forms of nitrogen, such as nitrite and nitrate. Okay? We're measuring nitrate, nitrite, and ammonia in our samples. Right? So we'll be able to create a diagram like this based on the conditions we see in the cenotes, and then take our samples, plot them on this diagram, and see, right, do they show up where they should, right? Based on, this diagram is created based on equilibrium thermodynamics. Now, if we see something, say like we have samples that plot on here and, you know, our conditions tell us that we should be up in this part of the diagram based on our EH and pH measurements, but we see a lot of ammonia, that tells me that the system is out of equilibrium, right? And tells me that there's something going on that is contributing ammonium to this system, right? That is, you know, that doesn't jive with the thermodynamic equilibrium that we're working on. And that's a clue, right? When I talk about creating that story. Phosphorus, however, right? There's no EH control on the speciation, as you can see here, right? The only control on the phosphorus speciation is pH, right? Because as I go from, say, 0 volts up to 1 volt, it's all the same species. Same here, and same here. And the only thing that changes, right, is due to the changes in pH. So the number of hydrogen atoms that are in each of the compounds. So since the speciation of phosphorus is not changed by the EH, right, we just want to know the overall concentration of phosphorus in the system, and we'll be doing that. But because nitrogen is sensitive to EH and pH, right, both the concentrations and the types of nitrogen, right, that we see are going to be important as we try to put this story together. So we'll be making measurements using spectrophotometry, right, which is kind of like an idea of you shine light through a sample, right, and you add some reagents that cause a color change or some change that change the absorbance of light through the sample. It's a fancy little brand new instrument that we just got. So we're excited about that. And there's different methods, but we'll be measuring, right, nitrate, nitrite, and ammonia. So those things that we saw on the EH-pH diagram for nitrogen. We'll be measuring phosphate. We're also going to measure alkalinity, right? We need alkalinity for doing the thermodynamic modeling that we're doing. Alkalinity is basically a measure of how much carbon there is, dissolved CO2 there is in the system is one way to look at it. And a new thing we'll be doing this year, which I haven't done before, is measuring total inorganic nitrogen, okay? Now, this is an inorganic form of nitrogen. This is an inorganic form of nitrogen. This one is an inorganic form of nitrogen. So we'll be measuring all these, and it'll be really interesting to do this measurement, which doesn't care what form it is. It just says, I want to look at all the inorganic nitrogen to see if the total inorganic nitrogen jives with when we add these 3 things up. Are we missing something, right? Or is something going on? So in terms of the spectrophotometry, the main things that will require is doing some wet chemistry to create some solutions of known concentrations, right, to make standards. And then generating what is called a calibration curve, where we plot the absorbance of light in the sample versus the concentration in our standards to create a line, right? We get an equation from that line, and then we can use that equation to calculate the concentrations in our unknown samples. Okay, so there's some wet chemistry work, there's a little bit of a computer work, and to do this, and then learning the different procedures for the different analytes, which are pretty straightforward, but we definitely want to have time to learn all of those. And then we're going to collect samples to bring back here, right, to do that major ion chemistry that I talked about, right? We're going to do that using ion chromatography. And Diane, I think on Friday morning, you're going to meet with Ashley, who I don't know, but we'll get to know her, and she's going to introduce you to the ion chromatography system here. But there we'll measure a set of cations, positively charged things, calcium, sodium, potassium, magnesium, and a set of negatively charged things, anions, chloride, sulfate, fluoride, and bromide, right? These are important for the geochemical modeling that I'm talking about, but will also be used when we start to look at where does this groundwater flow, where does it come from, what has it encountered, right, to try to put those things together. So in terms of the ion chromatography, again, making standard solutions, generating calibration curves, working with some reagents, right, and learning basically how the machine works and the techniques, right, that are involved in using it. So once we have all this, right, it's going to give us enough information, right, to interpret what's going on in our sites in terms of the geochemistry, right? And as I said, although we're super interested in these two guys, nitrogen and phosphorus, in order to look at the EH-pH diagrams and do other things, we need all those other parameters to give us the information that allows us to make those interpretations, right? So in terms of data analysis, right, we'll be using that program Geochemist Workbench, and right, it uses thermodynamics and equilibrium concepts, right, to figure out what's controlling the nutrient speciation in our systems, right? And as I said, right, when we look at nitrogen and phosphorus, are those species in equilibrium with EH and pH? Do they match what's predicted in our diagrams, or is there something else going on? Because if there's something else going on, right, that is very interesting, because we expect these systems to be in equilibrium, right? And if they're not, then we start to dig and try to tell the story that we're after. In terms of the major anion chemistry, right, we can use a couple different types of diagrams. One is called a Piper diagram, which is commonly used in groundwater studies and surface water studies, where there's these different plots, right, where you plot magnesium, sulfate plus chloride, calcite plus magnesium, sulfate, chloride, and calcium on these diagrams. And groundwater or surface waters that have different sources, right, or have encountered different rocks or different soils throughout time will plot in different places. For instance, on this diagram, the Amazon River is the black circle, the Mississippi River is the blue triangle, and the world average is the red triangle, right? And so as we look at these systems, we might be able to see there's some groupings of some cenotes that match each other based on their major ion chemistry, and some that don't. Another type of diagram that we'll use is called a stiff diagram. And it's a really cool visual representation of the chemistry of the groundwater system. And what it does is it just plots these anions and these cations, right? And they're plotted on the same scale of milliequivalents per liter, which we'll talk about. And you get this shape, right? That kind of if you know what's plotted on it, the shape gives you some idea of the major ion chemistry. And what's cool about a stiff diagram is you can do it in a lot of different places, right? Like here, then you can plot them on a map, which I think we should talk about in terms of what we talked about in terms of a little bit of mapping and things like that, to see how that major ion chemistry of groundwater changes in a region. And when you step back at it, right, you can just see by the way the shapes change that there's some, in terms of that chemistry, there's some different things going on here, right? You'll notice like in this region, right, these have a similar shape, but when I get over to here, these have a much different shape, right? So just visually, I can see that there is something going on with the groundwater here, and it's an interesting story to try to figure out. So all of that, right, the data, the modeling, allows us to compare what we observe, what we measure, right, with the equilibrium thermodynamics in these systems. And then the Piper and Stiff diagrams, how is the chemistry of groundwater related between different locations? So, we're going to be doing field work, we're going to be doing lab work, working with different types of analytical equipment, learning a variety of methods, doing some wet chemistry, and we tend to generate a lot of data, right? So one sample will have all those different things measured. So organization is important, because it's easy to get lost in your data. So easy. And working on data analysis, which is always something that I continue to try to work on as well. It's really easy to get focused on collecting the data, and I'm not saying it's not important, but once you have it, then you got to be like, all right, what does this say, right? Because it feels like it's a major hump just to get the data. Like, I have this beautiful spreadsheet, it's got all the data, this is all I need to do, but there is this additional step, right, that is equally or if not more important to, like I said, to tell that story, right, to recreate that story that your data is trying to tell you. So, overall, we should be able to tell that story, right, for our different field sites, how much nitrogen and phosphorus, what forms, what controls the amounts. Is there anything that we can say about potential nutrient pollution? If yes, what are some of the potential sources? And then, as Mel mentioned, how do we connect those results to the other projects? Like one that I'm always interested in is the geophysics project, because the geophysics project shows where there are fractures in the rock and how the groundwater moves, right? And so that is something that I'm always interested in, because that could really inform what we do here. Okay, that's geochemistry. Any questions, comments?
Okay. Come on in, Jackie.
I was here a while ago, but I didn't want to interrupt your very exciting.
So let's see if we can stop the recording and do the next one.
Any questions? Yes?
So, like.
You have to tell me your name, because I still need to know your names.
Rosario.
Rosario, thank you.
Okay, so I have two questions
Yeah.
actually. So one is like, how is like the flow determined? Is it based on like how much alkaline water, no, saline water exists?
Mhm. So groundwater flow. So there's a few different ways to do it. If you're near the coast, you can definitely look at the salinity of the water to see if you're getting influx from the ocean. But in general, determining groundwater flow is done in a myriad of ways. The easiest one to do, which doesn't work too well in our field area, is to measure the elevation of the water table in one area, like how high it is, and then measure the elevation of the water table in another area. And if it's higher over there and lower over here, right, the water will flow from the higher area to the lower area. However, in our field site, the change in that water table height over the course of the region is
It's very small.
very, very
Because
small.
of how flat.
Yeah,
Mhm.
so it's very difficult to do it that way. But part of the geophysics work is that through the measurements you'll be making, you can actually detect if there's groundwater moving underground. So that gives us a very fine scale kind of picture of what we think might be happening with the flow.
Yeah, and then we can also figure out how far below the ground surface some of the water levels are with your geophysics. And then what we can do is using some of the GIS equipment that we're bringing in to get the elevation of the ground. And then so we might be able to get some of those measurements. So that's one of the new things we're doing this year is bringing in some new GIS and some of those type of things with the geophysics to see if we can get a better handle on how that groundwater is flowing. So you guys are part of our new team. That's where Jackie and that team is helping out with it, is really working with the geophysics team to kind of get at that question, because we've really been struggling. I also have some what are called pressure transducers. So you put them into the water and they measure water level automatically. And so we'll put those into a couple places to see tidal movement and see if we can relate that also to some of the water flow. So yeah, it was a great question.
Yes.
It's one of the things we've been like wanting to do for
And you can
years.
see we're coming at it from lots of different directions. And you had another question.
I was wondering, what is bog water?
Oh, bog water is like swamp water. Like, so like water that kind of sits, like you think of if you picture a swamp, it's just sitting there. There's lots of vegetation that is decomposing in the water. The water tends to be very brown looking. There's lots of muck, right? So that's a place where you have lots of decomposition of organic water that drives down that EH or that oxidation state in the water. Mhm.